Okay, we're gonna get started here. Alright, so today we're gonna talk about ensemble methods. This could be relevant for Mini Project 2 if you're looking for that final push for accuracy, if you're really hoping to get high score in Mini Project 2. And this will also be the last lecture from the kind of Unit 1 in some sense, where we're just discussing supervised learning. Next lecture, so a slight change based on the schedule that's up. I'm going to change it. We're actually going to start next lecture with neural networks, which will begin the second major unit of this course, which is neural networks and deep learning. So far we've talked about supervised learning, so doing regression, doing classification. Yep. Yeah, yeah, yes. Okay, so where is it delayed by 24 hours? It's in the on the course on the schedule. Yes, sorry, the schedule needs to be fixed. Sorry, that was updated but updated incorrectly, and also needs to be switched based on what the schedule next lecture is going to be neural networks, not on PCA. So yes, the mini project has been delayed or extended by 12 hours because Kaggle has a downtime right on the day where the assignment was due. So it's poor timing, but I guess it's lucky for you in case you need that extra 12 hours. And I think in principle that means you get two more submissions. So I guess lucky for everybody. I think if you did two submissions in the morning and then two submissions the next day, I'm not entirely certain there. So yes, mini projects have been extended by 12 hours. So that's reflected on the assignment submission page in my courses, but it sounds like there's still the schedule on the course website needs to be fixed. The other thing I'll quickly say about this, I posted some kind of hints and clarifications, but I'll reiterate a couple right now, and probably the most important one, which is that if you're really submitting things to Kaggle and you're getting around 50%, it basically looks like you're doing random. It's probably not that your model's broken, it's probably that you're loading the data wrong. So this has been a issue that's came up a few times, and at this point the assignment's due kind of at the end of this week, and it's probably good to move beyond this kind of data loading issue. So if you're still having trouble with this, I'll talk to you after class today. I can talk to you in my office, so I kind of have extra office hours just for this issue. But I will say that, just to clarify right now, if you are having this issue where it seems like you can't get above random on Kaggle, but you're doing pretty well when you're doing validation tests yourself, this is probably due to the fact that when you're loading the test data, you're loading it in a random order. So unlike what you might presume when you iterate over a set of files in Python, so for example using the os.listdir function, there's no guarantee in the order that you iterate over those files. So we give you a bunch of files that are example 1 up to example 25,000, the different test examples, and you're supposed to submit predictions for those. Depending on your file system, depending on your operating system, things like that, if you're trying to load those files, you can't guarantee that you'll iterate over them in a nice way. So to make sure that you're actually loading the test data in the order that makes sense, there's two kind of basic ways to do it. One is you can say, okay, let's iterate over all the files in the test directory, but let's not just read them, let's also figure out what the file name is that we're reading, and then save that information. So that's option one. Option one is you iterate over all the files, you figure out, okay, I just loaded file 13, and now you say, okay, now I have this review, and I also have what the ID is for this review. So again, you can't guarantee that this load here, that this os.listdir, where we're iterating over all the files in this folder, we can't guarantee this will be in any sensible order. Really depends on things under the hood in your operating system, and most of the time is not reliable. The other thing you could do is you could just say for I from 0 to 25,000, load the file named stringi.txt. And then you're guaranteed to have loaded these things in the correct order. So I think hopefully by now this has been resolved for most people via office hours, things like that, but I thought I'd bring it up here just because the goal of the assignment is to do the machine learning and not to wrangle Python file loading too much. So that's one point there. Any questions on that? No? Okay. The other clarification point is that there is no minimum accuracy requirement for your naive Bayes model. I've said you should be able to get in the low 80s. And then there's people who are worried about, well, what is the threshold? What's the cutoff here? The threshold here is you have to have a correct implementation of naive Bayes. So if you have a correct implementation, but you're not doing very good text preprocessing, and your model's only getting 75, we're not going to take off points. It's about you having correct implementation of naive Bayes, and then the thing that matters for the competition on Kaggle is your best model. So you probably don't want to be submitting your simple naive Bayes model as your best model to Kaggle. So there's no requirement that you run your naive Bayes model on Kaggle. There's no requirement that it has some particular accuracy. I put my accuracy up there as a reference point, and for reference, the naive Bayes numbers that I put up there were using all words, so I didn't do any kind of pruning of the vocabulary, and I also did Laplace smoothing. So, and I did some pretty standard text preprocessing, I believe, with NLTK's default tokenizer. This was a TA who ran that one. So that's another point. If your naive Bayes model is working, but you're like, oh, I'm not getting 85 or really high, it's probably time to move on and work on a better model, work on some scikit-learn models to try to get your accuracy up. The other thing, I think this is partly a clarification point, but an important one, is that there's been, so first off, a couple questions about, well, can I use information about the test set, say, to compute IDF weights? Or say you want to use the test set to just compute some statistics. Obviously, you're not looking at the labels. That's actually not good practice and technically not okay. So you shouldn't be using the test set information about the test set at all, even for computing IDF weights, building word-to-vec vectors for people who are kind of jumping ahead a little bit and doing things like that. So this is the point where, yeah, you're really supposed to treat the test set as something you haven't seen before. The only way you're interacting with it is when you're making predictions on the test set. And this is important because it's not really a minor point, because if in a machine learning paper, say you were trying to get published, or something you were trying to do in a company to try to justify running a model in production, if you were using information about the test set, that would really invalidate your results. So in the kind of academic setting, that would be viewed as in some sense cheating. In the industry setting, that would be viewed as kind of not having a valid model, because if your model is going to run in production, it's obviously going to be making predictions on things it hasn't seen before. So using information about the test set to help build your model is definitely not okay. And related to that, I do know that though this is a public data set, it is possible to find the labels. It's possible for you to manually label things in the test set. That is all definitely not okay. So even though you might be able to get a little bit better on Kaggle if you do some not okay things with the test set, that is definitely not worth it, because we do know how well different models should perform on this data set. I know this data set quite well. I've worked on it for a few years. So I do know if you say, look, oh, we got 97 on Kaggle, and then you say you use Model X, and I know that Model X really can't do that well, that'll be an obvious red flag. So just to point that out, I mean, this is supposed to be, for the fun of the competition, and again, getting above my baseline only requires stuff from the course. There's definitely no need to look at the test set to beat my baseline. So just to bring that up, you shouldn't even use the test set even for computing IDF scores. Totally okay if you were confused about some of these things, and maybe we're looking at a little, just at this point, make sure the final thing you submit to Kaggle doesn't have anything to do with the test set. You weren't using any test set information at any point. Any questions on that? Cool. And then finally, before we get to today's lecture, one more clarification. This is relevant to today's, or this week's quiz. So in the lectures on SVMs, I think, frankly, I didn't do the best job explaining the impact of C when we're doing a soft SVM. So one of these SVMs where we have this trade-off between our misclassification, which is how much we're misclassifying here, these zeta terms, as well as our margin. And part of this was that, so I think that the short important thing to note here is that C does help us trade off between like overfitting and underfitting and bias and variance, just like the regularization term when we're doing L2 regression. Although in this case, when we increase C, this is going to actually make our model care more about doing a good job classifying the training point. So we're increasing C. This means that we're paying more attention to this misclassification term, which means that we're going to tend to, overfit the training set maybe a bit more and have lower bias and higher variance in general. And then last lecture, I talked about, well, setting C to 0 has some funny implications. In fact, setting C to 0 kind of breaks the soft SVM. So I think the intuitions for when you're setting C to 0 aren't a good thing to go with. The optimization no longer really makes sense once we set C to 0, because then we have these terms, these zeta terms that are unconstrained. So the important thing here is that C is like the lambda term in L2 regularization, but it goes in the opposite direction. So if we make C really, 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 really big, that's going to mean that we care a lot about classifying the training data well, which means that we're going to tend to have higher variance, possibly more overfitting. That's a clarification point, possibly very relevant to one of the quiz questions this week. Yep. Yeah, so this is the same thing I got myself into with the setting C to 0. I don't think it's possible. I think that the hard SVM would be when all of the zeta terms are 0, so they all disappear. That would be equivalent to the hard SVM. So there's no real way, I think, setting C to 0 or setting C to infinity are interesting thought experiments, but they break the optimization and no longer does things that make sense. So I'm going to punt on actually directly answering that, because that led me to say some confusing things last lecture. So yes, I think C has to be a number that is non-zero and non-infinite for this model to make sense. Cool. Okay, so moving on to the content of today's lecture. So today what we're going to be discussing are ensemble methods. So far in this course, again, we've really been focusing on this supervised learning problem, supervised regression, supervised classification, SVMs, logistic regression, naive Bayes, etc. So now in the final part of this, the introduction to supervised learning, we're going to discuss the idea of how we can actually combine different supervised learners, so different models together, into what's called an ensemble. So what is ensemble learning? Well, the basic idea here is we're going to run some number of learning algorithms, maybe the same algorithm multiple times. We're going to run this algorithm, say k times, and then we're going to somehow combine the predictions made by all these different runs into one final output prediction. Now, why might we want to do this? Well, a lot of algorithms have varying strengths and weaknesses. We might want to combine their predictions together so that they can complement one another. There's a lot of reasons why we might want to ensemble. As we'll discuss, ensemble learning can be a very effective way to reduce variance, so to try to combat things like overfitting. And in practice, ensemble learning is one of the most powerful techniques for getting raw, high accuracy or low error results. So if you want to just, say, win competitions, or if you look at who tends to win, big Kaggle competitions where they actually run these things for money, almost always there's an ensemble involved. And generally, actually, in the kind of machine learning academic community, the standard practice now is that if you're trying to say, look, my model's the best on this data set, generally we separate out results that are a single model versus results that are an ensemble of models, because it's not really an apples-to-apples comparison. So there'll be oftentimes even two leaderboards, where it's what is the best ensemble result on this benchmark. So say there's a famous benchmark right now for question answering, where the goal is we give a model a paragraph of text and we have to answer a multiple choice question from it. So right now, when you look at the leaderboard, there's kind of a distinction between the ensembles, where people are running a bunch of different models and combining them together, versus the single model accuracy. So generally in the academic community, we're mostly concerned with single model accuracy, but in terms of actually making things work in practice, ensembling is extremely important. So this is where the applied part and the applied machine learning in this course really comes in. So in terms of ensembling, there's 3 classic approaches, and this is what we're going to talk about today. So the first option is an approach that's called bagging. Here, what we're doing is we're constructing K models using the same algorithm, but on different random subsets of the training data, and then we're combining these models together. And when I talk about this is actually a theoretically and statistically well-motivated thing to do. It's kind of a funny idea. We're basically just training a bunch of different versions of, say, logistic regression or a decision tree on different random subsets of our training data, and then combining the output together. The next approach we'll talk about is something called boosting. So in this bagging idea, we're just training these models independently on different subsets of the training data, combining them together. This doesn't really, we're not sharing any information between these different methods. It's a pretty naive thing to do. In boosting, it's a slightly more sophisticated idea. And in boosting, the idea is that we're going to incrementally train K different models, where when we train the, say, Jth model, this model is going to be trying to correct the mistakes that were made by the previous models. So instead of just independently training models, we're training one model, it does some things right and some things wrong, and then the next model we train is going to try to focus in on where our first model was making mistakes. And then it's worth mentioning here that these 2 options, the first 2 we'll discuss, they generally assume that we're actually using the same base learning algorithm, and we're combining the outputs of a bunch of these simple algorithms together. So in bagging, we're taking a bunch of decision trees and just training them on different subsets of the input data. In boosting, we'll discuss, we use some particular types of models generally, often decision trees. And we're training a decision tree where the decision tree, the second one we train, is trying to correct the errors made by the first, and so on. But these are ensembling for ensembling, the same method. So combining a whole bunch of decision trees or a whole bunch of naive Bayes together. The third option, which can be called stacking, is in some sense maybe what you intuitively think about when you think of ensembling a bunch of models. Here, we're training a bunch of different classifiers. They don't need to be the same model. They don't need to have anything to do with each other. They're just K completely distinct models. Each one outputs some prediction, and then we're combining all these predictions using what we call a meta-classifier. So that meta-classifier could just be, say, the majority vote, but we could also do something more complicated. So stacking is a very effective approach, and what we'll talk about towards the end, but it's actually a very intuitive idea. We're just having a bunch of models make predictions, and then trying to figure out what's the best way to aggregate those predictions. So beginning with the first option, which is the simplest but actually a pretty powerful technique. So to get an intuition for why this bagging approach works, it's called bootstrap aggregation, is what it's short for. We first have to discuss an idea called bootstrapping. So bootstrapping is a statistical idea that actually has a number of applications, but what is useful for in machine learning is bootstrapping is a way to take our training data set, the data set that we're given, and then to make a whole bunch of replicates of this data set so that we can get good estimates for, say, the error of our model or the variance of our model. So it's very similar to cross-validation, but it's motivated a bit more by some sound statistical theory, whereas cross-validation is somewhat of a very pragmatic approach. Bootstrapping is actually something where you can prove bounds in statistics when you're using a bootstrap approach. So all we're doing in bootstrapping, very simple idea. We have our training set, D. Now we're going to make a bunch of bootstrap replicates, so K different replicates of this data set. Or here we're going to say B different replicates of this data set to keep consistent with the slides. And each of these replicates is constructed just by sampling with replacement from our training set. So we have a training set that has 1,000 examples. We're just going to sample 1,000 examples with replacement from this training set to make one replicate. And we're going to do this B times. So all these replicates have the same number of training examples as our original, but they're going to have some repeated examples because we're sampling with replacement. Yep. Yes, that's actually a really good point, indeed. So since we're sampling with replacement, couldn't we end up with a singular matrix? Say if we're doing linear regression, that is true. And this is a case where, so really linear regression is in some sense the method that is most kind of impacted by that. But in general, the way that we deal with this is that we almost never actually run the very simple linear regression. You always almost are doing some amount of regularization, or you can also compute instead of the inverse what's called the pseudo-inverse. So this is a good point, and in general, linear regression is probably, off the top of my head, the only method that will completely break when you have a singular data matrix. So if you wanted to actually do this, you would have to actually either do some regularization on that or compute what's called the pseudo-inverse instead of the inverse on this. So gradient descent will still work. But it's just if you're trying to do the closed form solution, you'll have to do what's called the Moore-Penrose pseudo-inverse rather than just doing the inverse. It's a great question, though. Yeah? This is an interesting point. So is bootstrapping going to lead to overfitting? Not really. So odds are you're not going to overrepresent one point by a whole ton because it's still totally random. So you're not going to end up with a data set that has, training example 1 replicated 1,000 times. That would be very improbable. But the other thing that we're going to talk about is we're actually going to not use just one bootstrap sample. We want to use all B of these samples. And that's actually going to help us combat overfitting rather than leading to overfitting. But before we get to this ensembling approach, just to finish up this idea of bootstrapping, again, the idea is we're just making these bootstrap replicates. These are a bunch of different kind of variations of our original training set. They're just like the splits in k-fold cross-validation, but now instead of splitting our data, we're sampling with replacement. And this can be useful, just like doing cross-validation, because we can get estimates of our error using these bootstrap replications. So again, it's a little bit different because of the fact that when we're doing k-fold cross-validation, we're splitting our data, so there's some training points that are in this fold and some training points that we're testing on in every split. Whereas with bootstrap aggregation, kind of randomly, some points are going to end up in some replicates and some points aren't. But we can still do the same idea as cross-validation, where what we can say is that for any training point x, we can say which bootstrap replicates did x end up in, and then for those kind of splits of our data, we can make predictions on x, and then we can get our average, we can get kind of what's our average prediction for x by saying for all k kind of fake random training sets that we made that contain point x, what is the prediction we make for x? So we're going to make slightly different predictions because all these data sets have slightly different samples. And once we have this prediction, we can actually, for one, we can estimate the bias of our model. So we can say how far off is the prediction of our model. So the average prediction our model makes on point x, how far is this off from the true value for y? And the other thing we can do is we can actually estimate the variance too. We can say how far off is the average prediction that we make for y from the prediction made by any of these individual models. And again, this seems a little funny, this whole sampling with replacement idea. And instead of doing, usually what we would do is k-fold cross-validation, where we would segregate the points, but now we're random sampling and just letting that randomness kind of give us a random segregation of our points, where some points might end up appearing in k of our replicates, some might end up occurring in, k minus 10, so we can have kind of all kinds of weirdness. But the benefit we get from introducing this weirdness is that this approach actually is a statistically sound estimate of these two quantities. We won't get into the justification for that, but that is why this approach is a reasonable thing to do. I personally recommend that if you're trying to actually estimate how good your model is, standard k-fold cross-validation is just fine. But there are cases where if you're really trying to get good estimates of, say, the bias of your approach is a good example, doing proper bootstrap estimation in this style is a sound thing to do. But of course, we're not just trying to estimate bias and variance. That's the motivation for why people do things like the bootstrap. You also use bootstrap for computing confidence intervals, all kinds of things. But what we're going to use it for is for ensembling different models. And the idea here is that, well, we've created these B different replicates. So we've made all these different random replicates of our original training data by sampling with replacement. We've trained a model on each of these things. So here, that's what we did. We trained a model on each. But why don't we just combine the output of all these different models? So instead of just training one model, we're going to make B different random data sets that are just random subsamples or kind of resampled versions of our original data set. We're going to train a model on each of these, and then at the end, instead of making one prediction, we're going to make, say, B predictions, and then just take the average or take the majority vote of these predictions. So the idea here is that we're trying to make our model more stable in some sense. Because instead of just making the prediction based on our training data, what we're trying to simulate is we're trying to say, well, in reality, our training data is just some subset of all the possible data we could have for this problem. Right? In principle, we could try to collect more training data. In principle, the data that we've held out for validation or that for test could be a part of our training set. So there's no reason why the specific training set that we're optimizing on, why that's the perfect training set. And in practice, if our model is going to be changing a lot depending on our training set, well, maybe we want to simulate that. And instead of using just one training set, we want to use a bunch of different simulated training sets and then take the average result after doing that. So that's the motivation here, and you might wonder, well, when is this kind of thing actually going to help? Well, it's worth thinking about, again, first off, this motivation for why we do bootstrapping is that, well, this allowed us to compute, say, the bias or the variance of our model, and we said that we can get a good estimate of the variance of our model by comparing the predictions that we make using any one of these random resampled data sets to the average prediction that we make. Now, what we're saying for our way of ensembling things is let's just use this average prediction as a more stable estimate. Well, if you think about, well, okay, what would be the variance that we estimated now for this new, if we're using h hat as our predictor, well, our estimated variance of h hat is actually going to be 0. So the idea is that by doing this bootstrapping and retraining of our model or training of our model on a bunch of these different random simulated training sets, what we're doing is, in principle, we're reducing the variance of our model down to be as low as possible. Again, we're not actually reducing it to 0. Our bootstrap estimate is not a perfect estimate of the variance, but what we're doing is that we're training a model so that our bootstrap estimate of the variance is 0, and in principle or in general, this is actually going to lead to lower variance models. And this is going to be a very useful approach with unstable learning algorithms. So if we remember, I was talking about decision trees. One of the downsides of decision trees is if I made small changes to the training data, that can really change the final decision tree. In decision trees, there's a lot of arbitrariness. So we're choosing the thresholds for these tests. We're doing all these different decisions, and they all involve a lot of thresholds, a lot of very sensitive computations. And a downside of decision trees is that they're very unstable. They change a lot. If you change one example in your training set, that can totally change your tree. So what we're doing with this bootstrap aggregation is that we're training a whole bunch of decision trees on different simulated training sets that are all based off our original training set, with the idea that, yeah, it's unstable, but now instead of having one unstable tree, we have, say, 100 estimates of what this tree could differ if we just changed a few training points. And then we're averaging all of this together. We're averaging the final output together. So that's the theory behind why this approach works, and it tends to, again, work very well with unstable models, and decision trees being the biggest one. So this isn't that effective of an approach for, say, linear regression or logistic regression, but it is quite useful for decision trees and also nearest neighbors. So one nearest neighbor, also very unstable. So generally, in some sense, the more models you use, the more variance reduction you're going to get. This is going to be a funny thing with kind of all of these ensemble approaches to some extent, is that really it's hard. The main cost you pay by adding more things to your ensemble is time, is compute power. Generally, in principle, you could, not for this approach, but for some of the ensemble approaches, you could start to overfit by adding too many models in your ensemble, but that almost never happens. So here, the only reason why you wouldn't want to use more is because it takes more time. So generally, if you're doing bootstrap aggregation or bagging, you want to use kind of as many models as you can afford. Again, if your training set only has 100 examples, well, there's not going to be that many different kind of bootstrap replicates you can make from that small data set. But still, there's no reason to not use more, and more in some sense is always better from a variance reduction view. It's kind of like a regularization. So the more that you add, the more you regularize, but you don't pay a very big penalty. So it's kind of a nice approach, very, very useful. You don't get a huge gain generally, but it makes things more stable, and if you're willing to pay that cost, it's usually worthwhile. So I mentioned that this approach is really most worthwhile when we're talking about these kind of unstable or high variance learners. So decision trees are one I kept mentioning, and part of that's because there's actually a couple very famous algorithms that rely on this bootstrap aggregation type approach in the context of decision trees. These are slight variations off the basic idea, but they're very famous methods, and they're very useful methods. They're actually, these two techniques, what are called random forest and extremely randomized trees, are two of the best off-the-shelf classifiers that I have used kind of in all of my experience. So the first one is what's called random forest. It's a little variant on this basic bootstrap aggregation idea in the context of decision trees. So what we do is, well, we get k bootstrap replicates, we train k different trees. When we're training these trees, we're not going to use all the features at every node and choose the best test based on all of those features. We're going to just choose a subset of our features. So the idea here is that we're training k different decision trees, training each of these trees on a different bootstrap replicate of the data, but we're not using the regular, kind of the plain old decision tree learning. We're making this learning a bit more random by actually picking variables at random. So we're not searching for the best test, we're searching for the best test just within a random subset of all possible tests. So what this does is that we're actually introducing more variance into the learning process. So rather than choosing the best test, we're kind of adding a bit of noise in there. And this noise is actually going to serve to introduce more variance. So we're making the individual trees that we learn higher variance even more unstable, because now our tree is going to be different depending on which little m we sample, so which set of variables we actually sample. So that introduces more variance, but we're combating that variance through this ensembling process. So we have a bunch of high variance trees, very unstable trees, but then we're combining them together, and this actually, in the end, gives us a very powerful model. So this is kind of a funny idea where this bootstrap aggregation idea, it reduces variance, but again, it doesn't really help that much when we already have a pretty stable model, say like logistic regression, and it works best with something like decision trees. It's quite unstable, and so the motivation behind this algorithm is, well, why don't we just make decision trees even more unstable, even more high variance, and then do even more ensembling. And interestingly, this actually does better than plain decision trees most of the time. So it's not just a crazy idea, it works quite well. The other variant of this is called extremely randomized trees. And here, it's actually no longer explicitly relying on bootstrap aggregation, but it's a very similar idea. We're making k different trees, but now what we're doing is that we're only picking m attributes at random without replacement, and we're picking a random test involving each attribute. So again, when we were learning decision trees originally, we were trying to find the best test.
But now we're just doing kind of randomly sampling a bunch of candidate tests and just saying which of these is the best. So we have this random space that we're searching over. And then at the end, we're going to build our model until we get to a setting where every leaf or every node has n-min nodes. So this is very similar to this random trees. It's basically the same idea that what we're doing is we're training a bunch of decision trees that are kind of have randomness or noise injected within them. They're still learning reasonable things, but we're not learning the best tree. We're learning a random tree that's pretty good. And then we're ensembling a bunch of these things together. And generally, the smaller m is, so the less candidate tests we're evaluating over, the smaller our random set of things we can search over is, the more high variance our model is. So in the extreme case, if m was just basically 1, then we'd just be kind of making random tests in our tree. That's not going to do that well, but there's a trade-off here. And again, it seems crazy. We're basically crippling the decision tree learning. Instead of finding the best decision tree, we're injecting noise and finding the best decision tree we can, conditioned on the fact that we're only allowed to look at a small number of random tests. So this makes some very unstable, some very high variance models, but when we ensemble, say, 1,000 of these together, they work extremely well. So extremely randomized trees, random forests, are almost always better than decision trees in terms of having high accuracy, but they're a lot less interpretable. Yeah. So this is a good point, and we'll actually talk about that in terms of like what do you need to actually have any sort of use out of the things you're ensembling. They have to be at least a tiny bit better than chance. So if it's totally random guesses, your ensemble is going to be totally random. But in fact, with the next method we'll talk about, we'll show how basically what you can get is that even if each of your models is just a tiny bit better than random, by combining, say, k of these models together, your approach can have an error that is exponentially better than each of these individual ones. So you can kind of leverage the fact you have a bunch of weak models and ensemble them together to get something that's very good. But it does have to be better than random. If it's totally random, you'll just have totally random predictions. Great question. So in general, this bootstrap aggregation and these random trees, they're instantiations of kind of ensembling via randomization. And this is a place where randomization might seem like a weird thing to do, but it's actually something that works reasonably well in machine learning. And so here we talked about kind of this randomization in terms of doing bootstrap sampling and also having our random choices for our tests in decision trees. But this idea comes up in other places in machine learning, like you can do random feature selection or take random linear projections of your data to reduce the dimensionality. So instead of doing PCA, you can just project your data down to a lower dimensional space just using a random projection, not the optimal PCA projection. And oftentimes, these approaches work way better than you'd think they would. They're very fast, they're very easy, they're kind of painless to use, and generally, they actually act as a form of regularization. So introducing randomness in a variety of different ways, so for example, selecting random features, selecting random tests in your decision tree, this is going to do something like regularization. It's going to increase the bias of your model. It's going to make your model kind of more incorrect on average, but it's going to make your model more stable. So it's actually a reasonable thing to do in a large number of settings. Now, why is this not always the best thing to do? Well, first off, say if we're talking about the context of doing random decision trees, so these random forests, these extremely randomized trees, well now, instead of just running one decision tree, we have to run k decision trees, where k might be 100 or 1,000. So yes, we're getting these lower variance predictions, and we're getting this nice ensemble, but we have way more models now to evaluate at test time. Generally, they're really hard to interpret. So in decision trees, a big gain is you can look at the decision tree and you can say, okay, I classified this tumor as recurring because it had a radius of greater than 1.6. Well, now if I say I have 1,000 kind of random decision trees, and each one of them had a kind of weird random way of choosing what the label was for this point, you totally lost all your interpretability. So one of the big advantages of decision trees is lost. And same as doing random feature selection or random projections. Now it's really hard to actually explain to people why your model works well when you're just randomly throwing things away. And of course, this doesn't fix everything. Models can still overfit, even when you're doing randomization. So that was the first general approach, this bootstrap aggregation idea, where the key insight is that we're kind of randomly resampling our data and building models on these different random resampled replicates and combining their predictions together. And then we talked about two slight variations of this idea, still using this kind of randomization approach in the context of decision trees. So these approaches do work quite well, again, generally only used in the context of decision trees and nearest neighbor models. Now the next type of ensembling that we're going to discuss is an approach called boosting. And here with boosting, the idea is that instead of independently making a bunch of different random models that we're combining together, we're going to incrementally construct K models where the models that we construct are trying to correct the errors made by the previous models. So the idea here is that the new models, the new hypotheses that we're learning, should focus on the instances, on the examples that were problematic for the previous models. So what's the basic algorithm here, the basic kind of approach for boosting? What we're going to do is we're going to first take our training set. We're going to train a simple predictor for this training set. I'll formalize the kind of models that we want to use here, but you could in principle use any model. We train a model on our training set, and now we look and we say, what training examples did we classify incorrectly? And now we give those training examples a higher weight. We make them more important, and we train another model, where this model is paying more attention to the things that were misclassified or where there's a high error by the previous predictor. Now we repeat this whole thing n times, and at the very end, we combine all these things together in some way. This is the basic approach, and there are many variations of boosting. Today we're going to talk about the most successful variation of this. But before we can introduce that, there's a little bit of notation that is necessary. So what we're going to assume here is that we're going to assume we have our training data set, but we don't just have our training data set. Now we also have a distribution over our training data set. So you can think about the training process as we're kind of sampling training points and trying to do our gradient descent on these training points. And now we're going to think about there being kind of weights associated or probabilities associated with different training points, which means that we're not going to weigh them all equally. So usually when we computed our loss, we just said let's take the sum over all of our training points. But now we're taking the expectation with respect to some distribution. So we're saying what's the expected loss on our training data? And in the usual case, that's what we're computing, is the expected loss on our training data, where every point is equally likely, or weighed is the same amount. But now we're going to say that we might have different weights, different probabilities of wanting to look at different training points. So this is a slight modification where instead of having our plain loss function, and here I'm using J for loss function, I use L as well sometimes. J is the other very standard way of writing loss functions, and it's more common in the deep learning community. So as we transition to talking about deep learning, I'll use J more and more. But again, the idea here is that, like a regular loss function, say we're trying to compute the L1 or L2 error, the mean squared or the classification error, but we're weighing different points by different amounts. That's this P function here. Okay, so the other thing now is we're going to assume that we have a bunch of weak classifiers. Here I'm going to focus on the classification setting. I've kind of implicitly been doing that. You can do all of this for regression, but classification is a bit easier to talk about. So we're going to assume we have some weak learners. So what's a weak learner? What's a simple model? Well, generally what these are things like what's called a decision stump, which just means a decision tree that's just one decision or one node. So we're just saying, is the radius of the tumor greater than 1.6? Then it's going to recur. no, then it's not going to recur. So it's a very, very simple model, maybe a naive Bayes model with just one feature, a one nearest neighbor. These are very, very simple models, and generally what we mean by weak is that we're saying that these models have pretty close to 50% accuracy, or 0.5 accuracy. So we're saying that the error for these models is 1/2, so basically random, minus a small amount. So we're assuming that this gamma term here is a small number, and these models are basically slightly better than chance. And what we want to do is we want to have some way of taking a whole bunch of these seemingly very weak classifiers that are just slightly better than chance and ensemble them in some way so we can actually end up with a very good classifier. And to show you an example of how this kind of idea works, well, suppose we have our simple training set shown here, where we have our blues, our positives, and our red negatives. Now, if we train a very simple, so here what's called a decision stump, is we're just making one threshold and we're saying, okay, everything to the left of this is positive, everything to the right is negative. Well, this is going to end up with some error value, and this is looking forward is something we want to compute, that is how much weight do we want to give to this particular decision. But then what we do is we can say, okay, well look, we've misclassified these three, so we should probably pay more attention to those when we train our next classifier. So now we make these ones even bigger, we weigh them even more, and now we train another model. Well, now this one's going to be paying more attention to these three because we misclassified them in the first one. So now we've moved and we make another decision boundary. This new decision boundary has another error rate and another amount that we want to pay attention to it. And now we're paying even less attention. These 2 points we've classified correctly both times, so we don't really care about them anymore. But now we're misclassifying these 3 red ones. So we're going to learn another decision boundary. And at the very end of the day, we're going to take each of these decision boundaries and we're going to have some alpha that tells us how much do we want to look at this particular decision boundary. And we're going to get some combination of these 3. So we'll take a linear combination of these 3 decisions to get our final model. And in fact, in this case, we end up with a very good final model where we're actually correctly classifying everything. So it's a very simple model. We're taking these 3 decision boundaries and again just applying what's called the sign function here. So we're just classifying as positive if it's greater than 0, negative otherwise. What we did is we took these 3 simple decisions and combined them into a really good one, and to build up where we put these decision boundaries, we were trying to figure out which training points do we have to pay attention to because the previous models were misclassifying them. So this is the intuition, but the whole question is, okay, this sounds good, but how do we compute the amount that we're reweighing these points by? And also, how do we compute these alpha values that tell us how much we should pay attention to these different decision boundaries? So the way that we do this, well, there's multiple ways to do this, but the, in some sense, best way to do this in a very seminal work by Freund and Shapire called AdaBoost for adaptive boost. Also, I believe, for Ada Lovelace as well, who was one of the first programmers who worked with Charles Babbage, so it's kind of named for her, and also because it's adaptive boosting. So I'm going to go over this algorithm. This is actually the algorithm from their paper. This is a case where it's worthwhile actually looking at the original algorithm, and we'll go over it somewhat slowly and then try to get a bit of intuition for how this works. So again, the idea here is we're given some training set. We have a bunch of x's and y's, and then we have a weight associated with each training point. So this weight in their notation is d. So d1 is the weight of the first iteration. So the weight of point I is 1 over m. So we're giving every point equal weight at the beginning. And now, for a number of different steps, what we're going to do is we're going to train a weak learner. So again, this weak learner is just like a decision tree with a single node. We train this weak learner, and then we figure out what is this weak learner's error when we're using this particular d weighing function for the different training points. So what is the error where we're weighing the different points according to this d? And now we're going to compute what's called the weight of this weak learner, so this alpha value that tells us how much do we want to pay attention to this weak learner. This is going to be 1/2 times the natural logarithm of 1 minus the error over the error. And then we're going to update how much we're paying attention to the different points. Basically, for points that we classified correctly, we're going to exponentially reduce the amount of attention we're paying to them, where that's proportional to this alpha term. And then for points that we misclassified, we're going to pay exponentially more attention to them based on, again, this alpha term. And then we're going to make sure that this new weights that we have for all of our points, we're just going to make sure that it sums to 1. That's what this z term is here. So we're just figuring out how much we should pay attention to these points based on our current model, whether or not it classified them correctly, as well as how well this model did. And then we want to make sure that this d, this distribution, always sums to 1. So a lot of this might seem somewhat arbitrary. So why are we paying alpha equals 1/2 ln 1 minus epsilon over epsilon? Why is that the amount of weight that we want to give one of these weak classifiers? Why are we doing this exponential update? Well, we're not going to go through all of the theory here, and I'm not going to ask you to be able to reproduce the theory, but in fact, this approach is very, very well motivated, and I'll show you in a couple slides. It actually can give us guarantees on the error we have at the end, and in fact, the error of our final classifier. So our final classifier here is we're summing over all of our weak learners. We're weighing each of them proportional to this alpha term, and then we're just classifying basically as a majority vote over that. We're taking the sign function after we're adding all these things up according to their weights, so not just a plain vote, but a weighted vote. And you can actually show that using this approach, the error that we have by combining all of these is, in some sense, exponentially smaller. We get an exponential reduction in error relative to each of these weak classifiers. And this work actually won the Gödel Prize in 2003. So it's a famous work in machine learning because it's one of those cases where a machine learning algorithm was actually winning the prize, which is kind of the one of the computer science equivalents of, you could say like a Nobel Prize. There's the Gödel as well as the Turing Award. So this model is a very, very interesting approach, and what you can show, and again, I'm not going to ask you to be able to do these derivations. It did win the Gödel Prize, so it's a complicated thing, but the important thing here is that when we're combining all of these models together, the final training error that we get, so our training error is going to be at most, well, this is going to be for each of our decisions. We have t different models. This is basically, we're saying, what's the probability each one of them classifies it incorrectly? But the thing you have to worry about the most is this term over here. So this falls out of the math in the original paper, and then this is due to something called Jensen's inequality. You don't need to worry too much about all of that. What you need to worry about is that at the end of the day, the error that we have when we run this AdaBoost algorithm is going to be less than e to the power of -2 times the sum of how much, basically the error rate of each of our models. So what this means is that by adding more and more models, we actually end up with an exponential reduction in the bound on our error. So this is kind of a crazy idea, this AdaBoost approach. It's this idea that instead of trying to learn a complicated machine learning model, let's just take the simplest model we can come up with, which usually is this kind of decision stump idea where we're just splitting our space by a simple threshold. And just by combining a bunch of these extremely simple models in the right way, using the right kinds of weight, we can end up with a model that takes a bunch of predictions that are slightly better than chance and gives you something that is actually substantially better than chance, exponentially better than chance, in a way. The exponent here, we're taking a sum, so it's not like a really amazing exponential reduction, but it actually works really well. Yep. D? So D's role here is, so I should have made that clear because they use slightly a different notation than I was using in their paper. So D here is how much we're weighing each of the training points when we're computing the loss. and when we're training the model. So D is telling us how much are we paying attention to the different points. And we're updating D based on whether or not we're making correct or incorrect predictions on this. So say there was one point I that every single time we were making the correct prediction on. That means that every single iteration we're going to exponentially downweight how much we care about point I. So by the very end, basically we're going to be ignoring point I. If we're always making correct classifications on it, every time it's getting exponentially downweighted. So by the end, it's really not going to matter. And again, we're using this distribution D. It's telling us how much we're weighing each point when we're computing our loss. So both when we're training our model, as well as when we're computing our loss here. So why does boosting even work? It seems like a crazy idea. It seems like we're taking a weird, models that barely work and just kind of throwing them together in, albeit an intelligent way. So the idea here is that in this case, each of these weak learners has really high bias. Each of these weak learners is definitely not high variance. If I just have a prediction where I'm saying everything that's, has a radius greater than 1.6, these tumors are all going to recur and everything else is going to not recur, well, that model is definitely not perfect, so it's very high bias. It's very far away from probably the truth, but it's pretty low variance. It's, I could change the training set a lot, and not many things are going to cross that boundary. It's kind of a very, very simple, very stable, in some sense, approach. So these are high bias things we're combining now. Remember, when we were doing the bootstrap aggregation approach, we were trying to combine a bunch of high variance models and use the ensembling to reduce their variance. In this case, we're taking a bunch of high bias models, so a bunch of models that really aren't that good at predicting, but are very kind of stable and simple, and we're combining all of them together to do better. So boosting in this sense is a bias reduction technique. So a bootstrap aggregation, this bagging approach, was a variance reduction, whereas boosting is a bias reduction. And motivation for how this approach actually works. So in fact, the reason why we make these particular choices of how we're setting alpha and how we're re-rating the points, it actually has to do with trying to find a good approximation to the log odds ratio via a linear combination of our weak classifiers. So that's why we have logs and exponents there. It's because all the theory behind AdaBoost is motivated by how can we take a bunch of weak classifiers and combine them in a linear way to get a good estimate of the log odds boundary. So like we did with linear regression, with logistic regression. With logistic regression, we were trying to find a really good linear decision boundary to specify the log odds. So in this case, that's kind of what we're doing, but instead of fitting a linear function, we're fitting a linear combination of a bunch of simple classifiers. So that's the kind of motivation for where this approach came from. And one thing you might be interested in is, so if we think about, well, what would happen in this case as we add more and more and more weak learners, right? So this is the bias reduction technique, and as we're adding more and more of these weak learners, as we're adding more models to our ensemble, you'd expect it's going to reduce our bias, but you'd expect it also going to increase our variance. So I mentioned in the context of bagging, of bootstrap aggregation, that, well, you can, kind of add as many models as you want, and generally it's just going to give you slightly lower variance. It's going to be diminishing returns, but basically just as many models as you can afford is good. In this AdaBoost one, now that we have a bias reduction, you might be worried, well, presumably we're going to start overfitting if we add a whole bunch of these random weak learners. So if I added a million little decision trees together, you'd think I'd really start to overfit. And what you'd expect kind of is the classic thing where we'd see our training error go down, 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 down as we add a whole bunch of weak learners, but our test error would eventually start going up. So we'd have this classic overfitting. Interestingly, empirically, this doesn't really happen with AdaBoost. So despite the fact that theoretically you'd think, well, this is a bias reduction approach, so you'd think that as we're adding more and more models, we're going to get increased variance, we're going to start to overfit. This really doesn't happen. A typical run of AdaBoost is shown here, where your training error does go down and goes down to basically 0, but your test error doesn't start going back up. Your test error just plateaus. This doesn't mean that it's not possible to make AdaBoost overfit, it just doesn't really happen that much in practice. So this is again a case where if you're asking how many models should I use, how many weak learners should I include in my boosting ensemble, well, kind of the more the merrier, really. I mean, you might start to overfit, but almost always this approach doesn't overfit, and you can just keep adding more and more, and it doesn't help you very much. Again, your test error is just kind of plateaued, but it doesn't hurt you. So kind of a conjecture in some sense is that this boosting approach doesn't overfit. So part of the reason why is this particular algorithm something that won the Gödel Prize and not any other algorithm in machine learning? Well, part of the reason is that, for one, it actually has this really nice elegant derivation and motivation, something we didn't have time to go into. But the other thing that's very interesting about it is that it doesn't seem to overfit, and overfitting is really the bane of all machine learning, right? We're always trying to avoid overfitting. So the fact that this approach doesn't overfit makes it extremely kind of promising for a lot of applications, and for a long time, it was viewed as, in some sense, the best algorithm. It had this elegant motivation. It didn't seem to overfit. I think that in practice, it didn't always perform the best, but some combination of its mathematical elegance and the fact that it does actually do pretty well made it kind of the crown jewel of machine learning for a long time. Again, this actually came out in 1995, so it's been around for a while. But yes, it's a very interesting approach. Doesn't seem to overfit. These days, it's not as popular. Again, like a lot of the methods I've been describing, like SVMs, were similar to some extent. They did very, very well in, say, the 2000s, but now deep learning, the next thing we'll talk about, has kind of taken over. So now just to quickly contrast the two different ensembling approaches that we've discussed so far. So typically, first off, the important thing to remember is that the first one, this bootstrap aggregation, where we're resampling our training set a whole bunch, or doing some random kind of resampling and combining, say, with decision trees, training a bunch of models, and aggregating their output together, say by taking a majority vote. This approach is a variance reduction technique, generally, whereas boosting, the second thing we discussed, is a bias reduction approach. Generally, it's easier to do bootstrap aggregation. It's easier to do bagging. All you're doing is just randomly resampling your data and training a new model. And in fact, so in scikit-learn, there's a wrapper that will just run that sort of aggregation on the model you provide to it. Generally, it works well with, you can run the bootstrap aggregation or bagging with a large number of different models. You can do whatever model you really like. You can put in there. It's not going to give you huge gains, but it generally pretty consistently gives you a small gain. Pretty minor, but it's kind of pretty standard, pretty easy to use. You can just throw whatever model you want. Boosting, on the other hand, is a bit different because it's really designed specifically to work with these weak classifiers. And boosting can also have this problem where if a lot of data, so if you have noise in your label, so if you don't have a perfect data set, it's going to really start to pay attention to things that might actually just be errors in your training set. So say you have some example where there's 1% of things that are actually spam, you're accidentally labeling as not spam. Well, those things might have all of the features of a spam email, and so you're going to misclassify them all the time, and your model over time is going to pay more and more and more and more attention because we keep getting these ones wrong. So AdaBoost or boosting in general is probably not a thing to use if you don't have clean data. If you don't have clean data, you're going to end up having the model try to work super hard to correct errors that aren't really errors. And again, the other thing with boosting is that it's not really an approach to ensemble a generic machine learning model. It's an approach to ensemble these weird weak learners, like a naive Bayes model with one feature, or this decision stumps. It's not a general purpose approach, but it's still an ensemble because it involves the combination of a large number of different algorithms. So now we're going to talk quickly about the final approach to ensembling, which is a bit different. So in the first two that we talked about, this bagging and boosting, here they were ensembling, so we're saying how can we combine the output of a bunch of different predictions, but we're basically assuming that we are using the same model to generate these predictions. So when we did bootstrap aggregation, we were saying, okay, let's run a decision tree, say for random trees, or random forest, let's run a decision tree on a bunch of different bootstrap replicates and combine the output. Or for boosting, we have these weak decision stumps, and we're combining a bunch of these predictions together, but we're assuming we have the same model. But what if we just want to ensemble a whole bunch of models that have nothing to do with one another? So, for example, what if we trained an SVM? What if we trained a naive Bayes model? What if we trained a neural network? We'll talk about next lecture. Some nearest neighbors. And we think, okay, all these models are doing okay, and they're making errors in different ways, so presumably if we somehow combine the output of all of them in a reasonable way, we could do better. So this is maybe the intuitive notion of an ensemble, is just that I've built a bunch of machine learning models. They're all doing reasonably well. How can I combine them all together and hopefully do a bit better? Well, here the way that we handle this is using what's called stacking, and the idea is quite straightforward. All we do is we take the predictions made by k different models. Again, these could be any arbitrary model now. We're going to make predictions. We're going to combine these predictions using what we call a meta model, sometimes called a combiner, and then we're going to make the final prediction. So what is the algorithm here? Well, what we're doing is we're going to train k distinct base models. We could do this using whatever we want. So in fact, stacking actually generalizes this bootstrap aggregation, because we could use bootstrap aggregation to train these different k models. But say we train these k models, one's an SVM, one's a logistic, one's naive Bayes. There's some nearest neighbors using different numbers of nearest neighbors. We train a whole bunch of them. Now, using each of these models we've trained k of them. We're going to make a new training set where instead of having our usual input features, our features for all of our training points are the predictions made by the previous models. So what we're doing is we're saying, okay, we trained an SVM, and now we're going to make a new feature for our data point that is, what is the classification the SVM gives this point? Or you could even, if you want to have it maybe be a bit more fine-grained, you could say, what's the distance from this point to the margin, as well as the classification we make. So what we're doing is we're training k models, and we're using these k models to generate new features for our data points. So our features are the output, they are the probability the model assigns to it, and we can even concatenate all of this with the original feature vectors if we want. So what we end up with is that we're basically using a bunch of models to derive really complicated new features. And these are obviously going to be pretty good features, because if our original model got, say if one of these models got 80% accuracy, well, we could get 80% accuracy just by using that model's feature, that model's output. And now what we're going to do is we made this new data set where each of our training examples in this new data set is what is the output and what was the prediction made by our previous k models. Now we're going to train a meta model on this new data set. And generally this meta model is often just averaging or taking majority vote. You could also train a logistic or linear regression is pretty common. It's not common to use a really complicated model for your meta model. It's usually standard to use something simple like just taking an average or majority vote, or just using linear or logistic regression. And the other thing to note here that I put down here is that you can also stack this, right? You could do this whole idea, instead of training one meta model, you could train k prime meta models. And then you'd end up with another bunch of predictions that you could then use to train another meta model, and so on. Again, that's less common. It's much more common to just use a combination of kind of having a set of models and then one meta model. But this idea is actually pretty powerful. And it's really powerful when you have a bunch of different models that have complementary strengths and weaknesses. So I talked about in several lectures this idea of an inductive bias. So it's kind of what are the assumptions our models are making. So for example, naive Bayes makes this independence assumption. With logistic regression, it's a discriminative classifier, not a generative classifier. These nearest neighbors approach, they're this non-parametric, lazy learning. And all these different approaches, they have different assumptions they're making, they have different pros and cons, and sometimes these can be complementary. So the idea is that if these approaches are making errors, these errors might not always be on the same sorts of examples. So in fact, by combining the predictions made by 5 different models that all make different types of mistakes, we can do way better than just using one model. So again, the key thing here is that they should be complementary. It wouldn't make sense to just run logistic regression 10 times and then take the output of that and then try to do stacking, because that's basically just going to give you the same prediction 10 times. Yeah. This is a good question. So the question here is, so the intuition is that we really want to combine the strengths of the models, right? Ideally, we want to not to kind of be able to average away the weaknesses, the fact that, oh, k-nearest neighbors always classifies these kind of points wrong, but logistic regression gets those right, so let's listen to it. So how do we actually make sure that we're getting the combination of strengths and not the combination of weaknesses? That is why you might want to actually learn the meta model rather than just having the meta model be, say, averaging, and you can include, say, interaction terms as well, rather than just using the raw features of what was the score output by all of the base models. You could use higher order features that says, oh, well, I know that when naive Bayes says it's true, but then when SVM says it's false, that generally we should say it's true, and things like that. But still, at the end of the day, it depends on the quality of your meta model, the quality of your data, and there is a big risk of overfitting, I should say, with all of this. But this kind of approach can work extremely well. It's something that a lot of people who win Kaggle competitions do often employ, this idea of stacking. And this idea of actually stacking a bunch of simple decisions on top of each other is also going to lead us nicely into the next topic, which is neural networks and deep learning, which are really, in some sense, can be thought of as the stacking of a whole bunch of linear or logistic regressions. So that's all for today. You should know now the idea of ensembling, the idea of bagging or bootstrap aggregation. That's for variance reduction. We have this boosting and this AdaBoost idea. That's a bias reduction approach. Both of them are generally working with some simple types of models, usually decision trees or these decision stumps. And then we have this stacking idea, which is a very generic approach to actually ensembling things together with a meta classifier. Thanks.